Okay, we have just 1 minute left, so let us begin. Our today's speaker is Konstantin Druzhkov. You see the title. Well, the title is very intriguing, and I hope we shall understand what all this means. Okay, Kostya, you're welcome.
Oh, yeah. Thank you. Thank you for having me. And today I'd like to tell about a non-trivial conservation law with a trivial characteristic. Let me briefly discuss the context of my talk. Well, first of all, I'll show that the percentage operator given by this total derivative with respect to x of the potential modified GDEq equation given by the formula 2 doesn't originate from its cosymmetries. So this prosymplectic operator cannot be described by cosymmetry because we know that in general, we describe conservation laws in terms of cosymmetries. And in order to describe cosymmetries, we have to solve some equation. But this equation also gives us some other solutions, not only solutions that correspond to conservation laws, not only generating functions of conservation laws. And other solutions for normal systems, say for systems of solution equations, produce prosymplectic operators. So it would be nice to have a situation when we know for sure that all prosymplectic operators are generated by cosymmetries, so we don't need to solve the other equation that describes prosymplectic operators. And we can solve only one equation for both, describe both conservation laws and prosymplectic operators. Today, I will show that in this case, in this situation, this is not the case. The prosymplectic operator given by the formula 1 does not originate from cosymmetries. So it cannot be described using cosymmetries. And in order to get this operator, we have to solve a different equation describing prosymplectic operators. Yeah, besides, we will make the following conclusion that the one component conservation law given under the formula 3 for the overdetermined system, which differs from GDEq by the equation uy equals to 0. So the conservation law is non-trivial, and yet one of its characteristics vanishes on the system, and the conservation law is an element of the second page. So it's an element of the kernel of the differential D1 of the Wiener-Grodel spectral sequence. So the conservation law lives on the second page. It is non-trivial, but it has it corresponds to the trivial cosymmetry. So we have a different problem with cosymmetries in this sense, because the system 4 is not a system of evolution equations. And we don't have any general result that like any conservation law can be described in terms of cosymmetries for such system. It turns out that in this case, it's not true. The conservation law given by the formula 3 cannot be described in terms of cosymmetries of the system 4. And the relation between equation 2 and system 4. Oh, okay. And the relation between system 2 and system 4 is that we add an additional independent variable y, right? But we add it in a very tricky way. In a very simple way. Oh, yes?
A question. This system 4, does it satisfy this regularity condition? If something vanishes on its infinite prolongation, it is a C differential operator of these defining functions.
Well, I think so, yes, because we have just like each prolongation of the system is a smooth manifold, right?
Yeah.
I would say yes. We just eliminate uy from this equation and eliminate ut from this equation, so we don't have any problems with this object.
Okay.
Yes. Okay.
So, and one more question. One of its characteristics is uxy, but uxy is 0.
Right. This is the point. The characteristic vanishes from the system.
Yes.
So it means that the cosymmetry is trivial. In this case, the cosymmetry given by the restriction of this characteristic to the system is literally 0. We know that for such systems, we may face a situation when we have a cosymmetry which is not literally zero, and yet it represents a trivial conservation law. It corresponds to a trivial conservation law.
Yeah.
But this characteristic has literally vanished from the system, and yet the
Oh, yeah,
conservation law is
okay, yes, proceed.
Yeah, this is the main point, the main idea of the talk. Yes, and as you can see, the conservation law itself, if we interpret x and y as spatial variables and t is time, which seems pretty natural in this situation, then the conservation law describes the conservation of zero. We don't have any reasonable conserved quantity in this case. We have just some non-trivial. I mean, we have just zero, which is conserved in some non-trivial fashion somehow. But of course, the system is rather degenerate itself. We use this trick, we add an additional independent variable here, and the system itself is rather degenerate. But if we want to construct an example of this type, we cannot consider non-degenerate systems in some informal sense. They somehow must be degenerate. This conclusion is not rigorous, but it is based on a variational interpretation of this term. We can use the homotopy formula, the standard homotopy formula, not horizontal one or something like that, just usual homotopy formula in order to interpret the elements of this term. Informally speaking, the space of boundary condition has to be degenerate if we have non-trivial elements of this group on the second page, because there are some obstacles to compactly supported perturbations. The homotopy formula describes some perturbations. Namely, we can take something like initial condition, but compact one, and evaluate the corresponding integral of our conservation law on the initial condition. And then we can try to perturb this initial condition within the class of initial conditions, such that on the boundary of the corresponding Cauchy surface, the perturbation vanishes. The boundary is fixed. And in this case, the variational interpretation based on the homotopy formula tells us that if we perturb the initial condition, elements of this group remain indifferent to such perturbations. So the integral doesn't change. This means on some intuitive level that there must be some obstacles to compactly support the perturbation somehow. Again, this is just an informal interpretation. The interpretation is not that good. This is why I decided not to include it into the corresponding paper. But here I can try to explain somehow. Besides, we will discuss that the presymplectic structures, similar presymplectic structures of closely related equations, like of the same equation, but with different coefficient, with a different coefficient. Of the equation 5, it differs only in this coefficient alpha. If alpha is 4, then we have the potential mkdv. And if alpha is not 4, we have the corresponding equation. It also admits the presymplectic operator that looks the same. But all such presymplectic operators do originate from their cosymmetries, actually. So they are not, they do not give us an opportunity to construct similar conservation laws for similar systems. And the variational interpretation doesn't clarify the triviality of the respective conservation law for the system 6. So we use the same tree, consider the system 6, and the corresponding conservation law constructed in the same way. It's trivial in this case, and the variational interpretation, the story about degenerate space of boundary conditions, obstacles to complex support, and all that, doesn't explain the fact that all such conservation laws are trivial for the system 6. So only alpha equals to 4 gives something non-trivial in this case. I'll explain why it works only for alpha equals to 4, but the explanation is incomplete still. It is based on some scale symmetry, and that's it. So loosely speaking, we have the following situation. If this group is non-trivial, then the space of boundary conditions must be degenerate somehow, but only in a special way. And I don't know how to describe this special way, like completely or something like that. So this interpretation is rather informal. So once again, on this informal level, the non-triviality of this term means that we deal with a degenerate space of boundary conditions, but it is degenerate in a special way. So I don't know how to give more precise description of this special way. So let's begin with the talk itself. Let's denote by epsilon the potential modified KdV equation given by the formula 7. And epsilon means the equation itself together with all the differential consequences. Now let's adopt the notation 8. So we denote u as u0, ux as u1, uxx as u2, etc. The infinite number of derivatives. Then the variables tx, u0, u1, u2, and so on can be taken as intrinsic coordinates on this system epsilon. System epsilon is once again described here. So we just consider the original equation plus all these differential consequences of all orders. The distribution of this system, of this infinitely prolonged system, is spanned by the restrictions of the total derivatives dx and dt, and they have this nice form. So dx is just the restriction of dx with this overline, and the corresponding operator dt is given also here. We can encode it in this nice form. So I assume sum with respect to the index I here, for example, Einstein summation convention, just zero. I use it just as zero. Yeah, elements of the algebra of functions on the equation epsilon on the infinitely prolonged potential on KdV are smooth functions of a finite number of these variables t, x, u0, u1, u2, and so on. And for any function, we can introduce the concept of order of a function. For any function, we denote by ord f the highest order of the derivatives u0, u1, u2, and so on among its arguments. And for function of t and x only, we put its order equals to minus infinity. It's important to note that the total derivative increases the order of any function by 1, right? So we use this condition, and because of this condition, the total derivative increases the order of any function by 1. We can say so because of this condition. Then the kernel of this operator consists only of functions of t, because if a function depends on u0, u1, or something like that, then the order of this function becomes greater than it was, so it becomes not minus infinity. And such a function cannot lie in the kernel of this operator. So if a function lies in the kernel of this operator, its order must be minus infinity. It must depend only on t and x, but in this case, it's easy to see that it cannot depend on x. So the kernel of this operator is given by functions of t. It's also rather standard situation for such systems, for equations that have this evolution form. Scalar equations. Yes, let's introduce the corresponding pre-symplectic operator. The potential modified KdV equation admits the Lagrangian given by the formula 13. Admits means that the Lagrangian describes the corresponding Euler-Lagrange equation are differential consequences of the original equation, not necessarily the equation itself. And we know that there is a problem for scalar evolution equations to be Euler-Lagrange equations for some Lagrangian, but their differential consequences can be Lagrangian equations. So we consider the Lagrangian 13, and this Lagrangian gives rise to the pre-symplectic operator given under the formula 14. So if we consider the corresponding variation of this component, then we get the right-hand side. The right-hand side, it's easy to see that we have some total differential operator applied to the equation. If we rewrite it in terms of the left-hand side, the equation itself on the left-hand side and 0 on the right-hand side. So we have a total differential operator applied to the equation itself, to the section that describes the equation. And if we have, whenever we have such situation, we get the corresponding pre-symplectic operator. We just take this total differential operator, calculate its formally adjoint operator restricted to the system, and the result of the pre-symplectic operator, the corresponding pre-symplectic operator. This is how we get this pre-symplectic operator. This is how we can easily describe this pre-symplectic operator. Example. Yes, and the relation with the modified KdV equation itself is given by the formula 15. So we have this modified KdV equation, v equals to ux. If we substitute this v equals to ux into the modified KdV equation and integrate it once, we get the potential modified KdV equation. For the modified KdV equation, this operator delta, since they are related by differential covering one-dimensional, the operator delta determines a non-local parasymplectic operator, which can be interpreted as a local Hamiltonian operator. The relation between these operators is given by the standard formulas. If we have an isomorphism of equations, we can rewrite a parasymplectic operator of one of these equations in terms of the other one, using the same procedure in terms of linearization operator and its adjoint. We can formally rewrite somehow the operator delta for potential MKdV in terms of the MKdV itself. As a result, we get a non-local parasymplectic operator, or which turns out to be a local Hamiltonian operator of this equation. So this is why I use the name the potential MKdV equation. I just introduce potential into the MKdV and get the potential KdV. Yes. So now we need some operators in order to calculate everything. The linearization operator for the potential KdV given by the formula 16, and its adjoint formula adjoint operator given by the formula 17. It's nice to note that the operator 17 cannot increase the order of a function by 3 or more, despite the fact that we have third order total derivative here, but the total derivative with respect to t also involves some terms of higher order derivatives, of the form of higher order derivatives. And on the level of the third order, the corresponding terms cancel. So it can only increase the order of a function by 2 at most. And let me recall that a function C is a cosymmetry of epsilon if it lies in the kernel of this adjoint linearization operator. So if the equation 18 holds. So in order to describe the cosymmetries of this equation of the potential and KdV equation, we need to solve the equation 18. But we don't want to describe cosymmetries themselves, right? We want to answer to the question whether the parasymplectic operator is produced by cosymmetries. And this is why it's important to note how cosymmetries produce parasymplectic operators. And for systems of evolution equations, the formula is very simple. It coincides with the corresponding formula for jets, actually, because evolution equations are jets in disguise plus vector field and plus an additional independent variable which can be considered a parameter in this sense. Well, cosymmetries of epsilon describe all its conservation laws and some of its parasymplectic operators. And as we see here, parasymplectic operators are the same things as variational principles. Or maybe not as we see here, but it's true for systems of evolution equations. Parasymplectic operators literally the same things as admissible variational principles. So it would be nice to know that we can describe all conservation laws and admissible variational principles by equation 18, but we are going to prove that this is not the case for the potential and KdV equation. And the formula 19 describes how cosymmetries produce parasymplectic operators. So just the usual formula, the same as the formula for GS. And the linearization operator of a cosymmetry C is given by this formula, just under linearization operator. And the question is this delta produced by a cosymmetry? We are going to show that the answer is no. In order to answer this question, we need some extra machinery here. We need to introduce the Vinogradov's spectral sequence, because the final answer is given by some interplay between the descriptions in terms of total differential operators and the Vinogradov's spectral sequence. The interplay is very important. Without it, I doubt that it's easy to prove that the cosymmetry, that the parasymplectic operator doesn't originate from cosymmetries. Formula 20 describes Cartan or contact one forms of the potential and KdV. So here we have just contact forms restricted to the potential and KdV. This explains why here we have we do not have something like derivative with respect to t, but it's expression in terms of the intrinsic geometry of the system epsilon. And Cartan-1 forms are linear combinations of this form with these basis contact forms. They must be finite linear combinations, and the omega I are smooth functions of the coordinates on epsilon. We can describe the ideal of Cartan forms. So it's just the dual description for the Cartan distribution. We can describe the ideal of Cartan forms given as the exterior product of Cartan-1 forms and all other differential forms on epsilon. And the ideal is differentially closed. So because the distribution itself is involutive, the ideal is differentially closed, meaning that it's from differential maps Cartan forms to Cartan forms. The powers of this ideal, exterior powers of this ideal, give rise to the filtration 22. So here we have the Durand complex, the Cartan complex, the complex of like twice Cartan forms. I'll call them twice Cartan forms. The complex of thrice Cartan forms, and so on. The filtration gives rise to the corresponding spectral sequence, which is the Vinogradov's spectral sequence. I used the notation 23 for the Vinogradov's spectral sequence. And it's important to describe the interplay between total differential operators or their elements of their kernels and the abstract structures, geometric structures described by the spectral sequence. Well, cosymmetries of the potential NKDV are in one-to-one correspondence with these variational one forms given by this term. So for any cosymmetry, we have the corresponding variational one form and vice versa. And then the corresponding variational differential for one form is given by this formula. So if we have a variational one form, we can consider the corresponding element of this group, and the same relation between variational one forms and elements of this group and their variation two forms is given by this formula in terms of cosymmetries. So in terms of cosymmetries and presymplectic operators, we just get the same formula. Presymplectic operators of the potential on KdV that do not involve the total derivative with respect to t are in one-to-one correspondence with this presymplectic structure. So instead of equivalence classes of presymplectic operators, we can consider only...
Kostya, what is the difference between a presymplectic operator and presymplectic structure?
Yeah, I mean that presymplectic structures themselves are equivalence classes of presymplectic operators.
Okay.
Yes, but
yes.
Using this structure of coefficients, since we deal with a system with an evolution equation, we can describe presymplectic structures in terms of just presymplectic operators of a special form, namely the ones that do not involve the total derivative with respect to t.
Yes,
All of them are also presymplectic. Any presymplectic structure is an equivalence class of presymplectic operators. Each equivalence class contains a presymplectic operator, a unique presymplectic operator that doesn't involve the total derivative with respect to t. So we can describe presymplectic structures literally in terms of presymplectic operators instead of equivalence classes of presymplectic operators. And the presymplectic structure omega corresponding to delta, the operator delta, is not produced by a cosymmetry if and only if it represents a non-trivial element of this group. Because it is not produced by a cosymmetry. If it's not produced by a cosymmetry, then it doesn't lie in the image of this differential d1, right? But we know for sure that it lies in the kernel of d1. So d1 of omega is 0. If it is not produced by a cosymmetry, then it doesn't lie in the image of this operator. Then it survives to the second page of the Vinogradov spectral sequence, if and only if. So if we can prove that omega doesn't originate, if we can prove that delta doesn't originate from cosymmetries, then we can prove that the corresponding presymplectic structure survives to the second page of the Vinogradov spectral sequence for the potential NKD. This is what we are going to do. Yes, the Lagrangian of the potential in KdV is scale invariant. It's important, actually, in this case. I don't have a final explanation, like a very good explanation of this situation, but this scale symmetry controls the situation somehow. This is say. So the Lagrangian of the potential PDV is scale invariant. We have this transformation group. We do not scale U remains the same, but we scale T and X. Then the equation epsilon, the potential MKdV, the infinitely prolonged one, possesses the scaling symmetry X, given by the formula 29. Yeah, so we have these two terms plus the infinite sum of the operator. Of course, if J equals to 0, then we don't have the corresponding term here, right? Just the sum actually J is 1 because the coefficient is 0 if J is 0. But still, we have this scaling symmetry. I mean that this scaling symmetry doesn't scale U. The corresponding coefficient is 0. But it scales derivatives, and it's important. Because of this term, the scale symmetry scales the derivatives, ux, uxx, and so on, with the corresponding coefficients given by the order. In fact, given by the order of the derivative. Yeah, note that x cannot increase the order of a function, this scaling symmetry, and its characteristic phi is given by the formula 30. It's important to know that the presymplectic structure given this presymplectic operator is x invariant, is invariant under the scale symmetry. It follows directly from the fact that the Lagrangian is invariant, of course. But we can also demonstrate it formally, or not formally, but in a different way, because the reasoning about the Lagrangian invariance is also formal. So the presymplectic structure is x invariant, and we can see it using the formula 31, for example. It's a different way to see this situation. And this fact is very important somehow. Once again, I do not have a good explanation, like a really good explanation why it's important, but I see for sure like that in this case it's important. I will comment on it a bit later, once again. So now we need to describe the kernel of the adjoint linearization operator. That is, we need to describe cosymmetries. But we do not need to describe all of them. We only need to demonstrate that there is no cosymmetry which produces the presymplectic operator delta. In order to do so, it's convenient to use the commutator under the formula 32. Just very simple formula. And the simple observation given by proposition 1. Just some combinatorial observation that how we can switch to operators. The total derivative raised to some power that is applied a number of times, and just a partial derivative. This formula is very nice and helps a lot. It simplifies the calculation. And another helpful fact is given by the following proposition, by the proposition 2. If psi is any function, not necessarily cosymmetry, just any function, and s is greater than or equal to 1, is an integer, such that the order of psi is less than or equal to s, then we have the formula 34. We can be proved easily using the proposition 1. So it's nice to know that if s is greater than or equal to the order of the function, of an arbitrary function under consideration, not necessarily cosymmetry, once again, then we have the formula 34. So we just apply this adjoint operator to the function, and we can calculate the corresponding partial derivative. And it turns out that the result is 3 times total derivative with respect to x of the partial derivative of the function with respect to s, not us plus 2. Yeah, and the main result of this part is theorem 1, that the operator is not produced by cosymmetry. In order to prove this result by contradiction, we now assume that the presymplectic operator is produced by cosymmetry. So let's assume that the presymplectic operator is produced by cosymmetry. Then we have a cosymmetry that produces it, of course, and let psi0 denote a cosymmetry, such that the cosymmetry produces delta. And let k denote its order. Here, I do not assume that there is a unique cosymmetry that produces, just any cosymmetry. Let psi0 denote a cosymmetry that produces delta. Let me recall that delta is just the total derivative with respect to x. And let k denote its order of any cosymmetry, just some situation. of this type, just any situation of this type, any cosymmetry that produces delta, and its order is k. So direct computations of cosymmetries of orders less than or equal to 6 show that k is at least 7. K cannot be 6 or less than 6. It must be 7 or greater than 7. Now we need some technical results in order to prove the rest of the theorem 1, in order to describe the rest of possible orders given by this k. Lemma 1 tells us that there is a function a of t, this function of time of the variable t, and a function psi2, just some function, not necessarily cosymmetry, again, just a function, such that psi0 has this form. So psi0 is k's order function, and it turns out that its k's order derivative is linear with respect to the k's order derivative, and the coefficient is just some function of t, plus a function such that its order is at most k minus 2, and k is even. So lemma 1 tells us something about the structure of the presumed cosymmetry and the order k. The proof is very simple. It follows from proposition 2, from this nice formula given under the formula 36 once again, in this case, in this particular case. And the condition, we just use this formula, and we see that if we assume that psi0 is a cosymmetry, right? Psi0 is not just a cosymmetry, it's a cosymmetry which produces delta, actually. But in particular, it's a cosymmetry, then this term must vanish. So according to our assumption, it is 0. So the left-hand side must be 0. Then the right-hand side must be 0. And it's easy to see that in this case, we get this structure of coefficients, right? The first term, using this simple observation. The fact that this term has order, its order is at most k minus 2, follows from this condition. Because using this structure of coefficients, it's easy to consider this difference in the explicit form. Just write this difference in the explicit form. And on the right-hand side, we must have something like dx, not something like that, literally dx, right? And according to our assumption, we must have just dx. It means that the order of the right-hand side must be not that high, just the order total differential operator. So the higher order total derivatives on the left-hand side must vanish. And using this structure of coefficients, it's easy to show that it means that k must be even because of that. Because if k is odd, then the difference is k's order total differential operator. But we know that k is at least 7, and delta is just of the first order. The order of delta is 1. So this is not the case. It will not be the case. So using this condition, we derive this structure of coefficients. That is, we obtain the information that the order of psi2 is at most k minus 2, and k is in order to prove theorem 1, we need to show that actually the derivative of this coefficient is 0, so that it is a constant. It would be nice. Maybe it's not true that we need to show it, but it would be nice, at least in this case, to show it, because the rest of the proof of theorem 1, of my proof of theorem 1, is based on this fact. So I'm going to prove that a is actually a real number, so it doesn't depend on t, in fact. And this proof is rather technical. First of all, we show that there exist functions b and psi3 such that the structure of coefficients is given by the formula 37, where the order of this psi3 is at most k minus 3. The coefficient b is given by this formula. So now we're going to dig deeper into the structure of this cosymmetry, of its coefficients, of its dependence on order derivatives. using this, this lemma follows from the previous one, actually. We just apply the same thing as proposition 2. So we apply the same idea, but not for k, but for k minus 1 on the right-hand side, and for k plus 1 here. The same proposition 2. Then we get the corresponding lemma 3, so we dig deeper into this structure of coefficients once again. We find that on the level of, on the k minus 3 order level, we get these functions. So it's also linear with respect to u k minus 3, and the coefficient c is given by this formula. It is based on the coefficient b, and so on. So we needed only to demonstrate that a is a constant, actually. But in this case, somehow we have to, or at least I decided it would be nice to describe the structure of the coefficients, because using it I can show that a is constant. Maybe it's possible to show it in a different way, in a simpler way, or something like that. But at least this reasoning is a rigorous proof that a is a constant. Okay, so now we know that the structure of coefficients is something like that. We also need the following technical lemma 4. Lemma 4 tells us that if we apply this guy to one of the terms arising in this psi 0, if we calculate, because we can apply it to any function, right? The adjoint linearization operator, and the proposition 2 works for any function, not necessarily for a cosymmetry. So we can apply the same proposition to this term, and on the right hand side we get this, where f is some function. So the important part of the story is that on the right hand side we do not have something of the form like total derivative with respect to x applied to something due to this term. All other terms are of this form, but this term is not of this form. It's easy to see that this term is not dx of something, except for the situation when a dot vanishes, when a is a constant. And using this lemma, using this observation, and the reasoning of the same type, we finally get this lemma 5 that tells us, which tells us that psi 0 is of this form where a0 is a constant, finally. And of course, on this, at this point, we can say more about this term psi 1. We have more detailed version of this psi 1, more information about it, but actually we don't need it. So this reasoning was only for coefficient, to prove that the coefficient is a constant, is a real number. So note that the scaling symmetry acts on cosymmetries. Now we need to note that the scaling symmetry acts on cosymmetries. The action is the same as the Lie derivative in terms of variational one forms, and the action is given by this nice formula. So the Lie derivative in terms of variational one forms becomes just x plus 1 in terms of the corresponding cosymmetries. And the order of the corresponding cosymmetry cannot be greater than the order of the original one, right? So the Lie derivative cannot increase the order of a cosymmetry. This information itself is not that important, but it's nice to know, right? It's easy to see because of the structure of these coefficients, right? It cannot increase the order. X itself cannot increase the order. And here we have just x psi plus psi on the right-hand side. So the order remains either the same or it becomes just less than the order of the original cosymmetry psi. So it acts on cosymmetries in this form, and now we can get the final proof by infinite descent. Let me recall that we have this formula 45. We have this structure of coefficient for psi 0, and it's easy to see that if we apply x plus k to the highest order term, then we get 0. This follows directly from the structure of coefficients of x, from the symmetry itself. So here we get 0. If psi 0 produces delta, then this cosymmetry also produces delta. It's easy to see this fact because this cosymmetry corresponds to this variational one form. And we know that the Lie derivative of the corresponding presymplectic structure, capital letter omega, vanishes, right? So the Lie derivative vanishes. That is if that is why we have this situation. So if we apply this operator d1, the differential d1, to this variational one form, this term vanishes. It's easy to see because d1 and the Lie derivative commute. This term vanishes, and we just get d1 of this term, which is omega itself, the presymplectic structure omega. So it means that this variational one form also produces the same presymplectic structure. And in terms of cosymmetries, we see that this cosymmetry produces the same presymplectic structure. But the order of this cosymmetry is strictly less than k, right? Because x plus k of the highest order term is 0. So its order is strictly less than k. And we get the contradiction, right? So if we have a cosymmetry that produces delta psi 0, then we get a cosymmetry that a different cosymmetry that produces delta, and its order is strictly less than the order of psi 0. But there must be a lowest order cosymmetry psi 0, cosymmetry psi 0 that produces delta, and its order must be at least 7, the order of the lowest order cosymmetry that produces delta, because I do not imply that such a cosymmetry is unique. There must be a lowest order cosymmetry that produces delta, and this result contradicts to the computational observation that k is at least, right? Because in this case, for a lowest order cosymmetry that produces delta, this construction gives a cosymmetry that also produces delta, but its order is strictly less than the lowest order cosymmetry, the lowest order of a cosymmetry that produces delta. So it's a contradiction. Yeah, and the main result for the potential on KdV is that the presymplectic operator delta is not produced by a cosymmetry. So the second page of the Vinogradov's spectral sequence for the potential on KdV is non-trivial somehow, because of this presymplectic structure, of course, at least because of this presymplectic structure. So now let's consider this conservation law, the conservation law. The same Lagrangian gives rise to a differential two form, L differential two form on the equation, such that this form and the restriction of the Lagrangian, the difference between them is the Cartan form, and this coset represents the presymplectic structure. So the differential of L is a twice Cartan form, and the coset represents the presymplectic structure. This is the description of the relation between the Lagrangian and the presymplectic structure, not in terms of operators, but in terms of differential forms, or equivalence class differential form. So this form represents the corresponding internal Lagrangian. A different description is that this Lagrangian produces an internal Lagrangian, and this internal Lagrangian, the corresponding internal Lagrangian, produces the presymplectic structure. But it's important to note that the presymplectic structure is determined by the form dl, is completely characterized by the form dl. And due to this differential, it's easy to see that the element of this group of like Lagrangians on epsilon, not internal Lagrangians, but just Lagrangians on epsilon, but on the second page, surviving to the second page. The corresponding element determined by this form L is trivial, because its image under this differential is the presymplectic structure omega. The image is not trivial. It means that the element itself is not trivial. So the element determined by L is not trivial. This element coincides with the element of this group determined by the restriction of the Lagrangian because of this fact, right? The difference between them is a Cartan form. So on the 0 page of the Vinogradov spectral sequence, the corresponding elements with the same structure of coefficients 0, 2 are the same. On the 0 page, of course, they are on the second page as well, right? So now we know that the element of this group on the second page, determined by the restriction of the original Lagrangian, is not trivial. Yeah, due to this differential, relating it to the corresponding to the presymplectic structure. And we can use the following trick. We can introduce the system 52. Let me denote it by epsilon prime dy. So this system differs from the potential and KdV equation in one independent variable, but uy partial derivative, or the derivative with respect to this new variable, is 0. So the difference is not that huge, and we are going to use this fact, this observation, that the difference is rather special in this case. So to form the differential to form 53, which formally coincides with the expression for the Lagrangian L, like the same differential form, but interpreted in terms of the corresponding system, or the jets of the corresponding system 52, because the system has different jets because it involves an additional independent variable. So using the same coordinate expression, we get a conservation law, and the conservation law is represented by the form, or it is determined by the formula 54, because we can take this restriction plus d0 of anything, and here we can describe d0 in terms of as representatives of the corresponding elements on the 0 page. So let's take this representative, and it's d0, and it turns out that the sum of these forms is just this very good looking, very simple differential to form, one component differential to form. So this differential to form is the same conservation law as the conservation law given by this Lagrangian, because in terms of the potential KdV, we can interpret it as the Lagrangian. Now we take this lambda and consider the decomposition, dy of lambda. So we just apply the horizontal differential to L. We apply the horizontal differential to L, and in components, it is given by the derivative with respect to y of lambda, and we get this decomposition. It's easy to see that these terms given by dt and dx of something, they vanish on the system 52, right? Because here we have uy, here we have uxy and uy. So we have this total divergence that vanishes on the system 52. Then the corresponding characteristic, or a corresponding characteristic, is given by these coefficients of the equations of the system 52. And the coefficients are uxy and 0. So the conservation law is associated, for example, with the characteristic q. Q is given here. Its components are uxy and 0. You see that the corresponding cosymmetry, because the restriction of a characteristic of a conservation law to the system is a cosymmetry. So the cosymmetry is 0, right? Because this component vanishes on the system due to this equation, or due to its differential consequence. But the system is considered with all the differential consequences, of course. And this term is literally 0, this component is literally 0. So the cosymmetry is 0. This means that the conservation law either lives on this second page of the Avogadro spectral sequence, or trivial. So we have only two options in this case, because its d1 is 0. It lies in the kernel of the corresponding trait. Let me know that the systems epsilon and this epsilon prime dy are related. Namely, we have this direct product structure for epsilon prime dy for the overdetermined system. And actually, they're not just related by this observation. They are homotopy equivalent. And the homotopy equivalence is based on the formulas 56 on these two mappings. It's important to note that by the homotopy equivalence, I mean something like homotopy equivalence for differential equations, not just homotopy equivalence in the category of like homotopy of topological spaces with a point or something like that. I mean homotopy in terms of differential equations. That is, for any parameter value, homotopy parameter value, the corresponding mappings are morphisms of differential equations. That is, they map Cartan distribution to Cartan distributions. And using the homotopy equivalence given by these mappings, and the homotopy equivalence itself, it's easy to see the homotopy equivalence, right? If I take the composition, say, of this mapping and then of this mapping, the projection, at first I just set y equals to 0, right, and get this system, an embedding of this system. And then I consider the projection, so I get the original system itself. So the composition of this mapping and the projection is identical. And the other composition of the projection and then of this mapping is homotopy equivalent to the identical mapping. I just can take homotopy parameter here, right? Something instead of 0 here as a homotopy parameter. So they are equivalent, and this implies that their second pages are the same. It means that we have this equality. And the pullback of this mapping becomes an isomorphism on the level of the second pages. Then the conservation law of this system is non-trivial. Because for this system, the same term describes conservation laws. That's right to the second page, but yet it describes conservation laws. And the conservation law is not trivial because the conservation law is the pullback of the original Lagrangian, of the original element of this group, determined by the Lagrangian restricted to epsilon. So the conservation law is also non-trivial for this system. Now let me try to interpret this result somehow. And let n be a complex-oriented smooth manifold of dimension n-1, and let S be a system of differential equations with n-dimensional Cartan distribution. Just any system, not necessarily epsilon or epsilon prime dy, just a system of differential equations, any regular system of differential equations. Then we can consider embeddings of this compact-oriented smooth manifold with or without boundary. It doesn't matter in this case. Any embedding. And there are nice embeddings. We can say that an embedding is an almost boundary condition if it defines an integral manifold of the Cartan distribution C, n-1 dimensional. So the planes of the Cartan distribution are n-dimensional, but this manifold is n-1 dimensional. So it's not a maximal integral manifold, but yet it can be an integral manifold. We say that it's an almost boundary condition. Yeah, the words about almost boundary condition mean that we can consider not necessarily manifolds without boundaries. We can actually consider manifolds with boundaries. For example, for the heat equation, it's a very simple example. For the heat equation with intrinsic coordinates Tx, Ux, etc., we can take the following manifold n of the corresponding Tx submanifold of this Tx plane, just a segment of this timeline, x equals to 0. So it looks like a boundary condition for this equation, but not a boundary condition because time is restricted. This variable t is restricted. It lies in the segment 0 to 1, not in the real line. This is why it's an almost boundary condition, not a boundary condition itself. Not like a genuine boundary condition. And on this submanifold, we can consider the corresponding almost boundary condition. It has this form. It is given by two functions of time, C1 and C2. They can be chosen arbitrarily, and the rest of components of this section is determined by these two functions. So Uxx becomes a C1 because Uxx is Ut, and Ut gives us C1 dot, and so on. Arbitrary two functions describe almost boundary conditions for this segment. Or we can take a similar picture. We can consider this segment x from 0 to 1, the initial time moment, and then it becomes something like an initial condition, but of course it's not just literally an initial condition because we consider x restricted from 0 to 1 on the set line of the segment, not in real line or something like that. So it's an almost initial condition, but it can be considered almost boundary condition. And then an almost boundary condition itself is given by an arbitrary function h of x. U is h of x, ux is x, h prime, and so on. So it's a very simple, right? An almost boundary condition. Or we can set some condition on the circle, t squared plus x squared equals to 1 or something like that. Because in this case, n, these both copies of n, not copies, but just examples for n, they have non-trivial boundaries, or we can consider something without boundary, like circle or something like that. All of them are almost boundary conditions, but of course here we have to describe the almost boundary conditions somehow on this circle. It's not a problem, but I have no description here. And using this concept of an almost boundary condition, we can apply the homotopy formula now. So let M be a path in almost boundary conditions. So gamma, let gamma be a path in almost boundary conditions. Now here we have a mapping of M times the interval, and it maps function to S, so it's just homotopy. Homotopy within the class of almost boundary conditions. This is why we can use the standard, not this is why, but now we can use the standard homotopy formula. We can produce just a section of this form and write the standard homotopy formula for any differential form on epsilon. The homotopy formula, not on epsilon, on S, sorry, on S, on a given system, on a given regular system of differential equations. So the homotopy formula is given by the formula 65 in this case, consists of two terms. So the difference between the corresponding pullbacks along this along these almost boundary conditions, along two homotopic almost boundary conditions, the difference of the pullbacks is given by this combination, like just as usual. K of omega is given by this formula. And if omega determines a conservation law, Xi, that is an element of this group of S, and the boundary remains fixed, then we get the formula 66. The first term vanishes due to the requirement that the boundary is fixed, remains fixed, so it's unperturbed. Then we get the formula 66, and it's easy to see that the perturbation itself is determined by the variational derivative of the conservation law, because it's determined by the Durand differential for representative, right? And this observation doesn't depend on the choice of a representative, so the interpretation of d1 of psi is given by this homotopy formula. And the perturbation is given by d1 of psi. That is by cosymmetry of psi, right? So if the cosymmetry is trivial, then the integral functional is indifferent to perturbations of an almost boundary condition, it remains the same. We take the difference and we integrate the difference, right? Like here, and we get 0 on the right-hand side if the cosymmetry is 0, or if the corresponding variational differential is 0. So on the right-hand side, we have 0, and for any like homotopic parameter value, we get the same integral. The integral remains the same. It's important to note here that we can consider situations when n has a an non-trivial boundary, because if n doesn't have a boundary, then this boundary condition may normally it determines a solution, and if a solution is non-singular and the topology of some base space is trivial, then for the closed submanifold, for a closed manifold, we get just trivial information, because the difference becomes topological. If the topology of a base is trivial, the difference becomes 0. So if we restrict ourselves to closed manifolds, we cannot give an interpretation of cosymmetries or of d1 psi in terms of a normal situation, of a simple situation, only in a topologically non-trivial situation. And we would like to have an interpretation for any situations. And this is possible in our case because we can consider manifolds that have non-trivial boundary. They must be compact, oriented, and -1 dimension, but they may have a non-trivial boundary. So the integral function is indifferent to perturbations of an almost boundary condition, compactly supported perturbations, right? Because n itself is a compact manifold. Or one can interpret this situation as just we have an initial condition on the entire real line. So we have a system with t and x, and we have an initial condition t equals to 0 and some initial condition, and we perturb it on a segment, not on the entire line. So the initial condition itself lives on the entire real line, spatial line, but we can perturb it. And we can also describe the perturbation in terms of this situation, and the result is also indifferent. The integral is also indifferent to such perturbations. So we have some problems with perturbations of boundary conditions if the conservation law is non-trivial. If the conservation law is not trivial, but its cosymmetry is trivial in this situation. I don't know how to describe these obstacles to perturbations better, in a better way, but on some intuitive level, this is what we have. Some problems with like a possibility to perturb boundary conditions or initial conditions, to consider their compactly supported perturbations. But this interpretation doesn't explain the following observation. For the system, not the following observation. Let me be specific about these problems with perturbations. Let's consider the original system itself, the system, the most important system of this talk. We can take as n the disk. It must be two-dimensional, something two-dimensional. So let's take the disk with the boundary circle. The disk lying in the plane y equals to 0. Then sigma, being an almost boundary condition, must be a solution to the potential mkdv. But this solution to the potential mkdv must remain unperturbed on the circle, t squared plus x squared equals to 1. I doubt that we can perturb solutions of the potential mkdv such that the boundary, such that they, all of them, like, satisfy to the same boundary condition in terms of kdv itself, of the potential modified kdv itself. This would mean that we have a lot of different solutions to the same boundary value problem and all of that. This is why I don't know if it's true, but I think that on some intuitive levels, rather clear that we cannot. So we have some problems with perturbations in this example, right? Because we have to keep this condition that the boundary must be fixed. And if n is given by this disk lying in the plane t equals to 0, like the disk that gives us some initial condition, then the boundary is fixed if and only if the entire manifold is fixed. So we cannot perturb an almost boundary condition within class of almost boundary conditions. We cannot perturb it at all due to the condition uy must be 0. So this sigma, its components cannot depend on y. If in this situation, if the boundary of this disk, the boundary circle, is fixed, then the disk itself must be fixed. So we have some problems with these perturbations, compactly supported perturbations of almost boundary conditions. For example, this is why this interpretation explains something at first sight. But actually, there is a problem with this interpretation, because if we consider a closely related Lagrangian, given by this component lambda, where we have alpha instead of 4, just an arbitrary alpha, which is not 4, and let's say which is not 2. Then we can consider the corresponding system. We get the same presymplectic operator, which looks the same, for the corresponding equation given by the formula 71. It's easy to see that if it's 4, then we get the potential on KdV, right? And if alpha is 3, then we get just potential KdV, not potential mKdV, but potential KdV for alpha equals to 3. Then we can see that all of these equations, when alpha is not 2, all of them admit the following scale group, scaling transformation. This transformation, given by this formula, where beta has this form, scales our Lagrangian L tilde in this way with some non-trivial coefficient. So if alpha is not 4, then the coefficient is not 0. Then the corresponding presymplectic structure determined by this Lagrangian for this equation is produced by the following variational one form. We just contract the symmetry and the presymplectic structure divided by 2 beta, by this coefficient, and this variational one form becomes a potential for the omega itself, for the corresponding presymplectic structure. It's easy to see the situation, right? Because because the Lie derivative of this guy consists of this term with respect to x divided by 2 beta, consists of this term plus the other term given by the Magic-Cartan formula, but the other term vanishes because this is a presymplectic structure. That is, it's a D1 closed variational one form. So this is literally the Lie derivative of this term. And the Lie derivative of this term is proportional to the term itself because of this formula 73, because this holds for the Lagrangian. it's easy to see that if we calculate the corresponding Lie derivative, that is, we calculate the derivative with respect to epsilon, initial time moment, initial epsilon moment, then we have a non-trivial constant here, right? Non-trivial factor. So the Lie derivative scales Lagrangian as well. This means that the Lie derivative of omega is proportional to omega. And just using this factor, we see that the corresponding the corresponding present vector structure is actually variationally exact. So it cannot survive to the second page. Yeah, the symmetry itself, symmetry on the level of the corresponding infinitely prolonged equation, the symmetry have this form, yeah, and so on. And if alpha is 2, then we cannot use this scaling group because the corresponding equation does not admit the scaling group. But if alpha is 2, then it's easy to see that we get just a linear equation, right? We get the linear equation, and we know that for linear equations, all linear equations are homotopy equivalent to the corresponding base spaces. And in this case, our base is dimensional real vector space R2. Its topology is trivial, so it means that the corresponding second page of this equation is trivial, except for one term, which doesn't matter. I mean that presymplectic structures surviving to the second page of this equation must be trivial. All of them are trivial. So nobody survives to the second page in terms of presymplectic structures, conservation laws, and all of that, of course, because the equation is homotopy equivalent to the base. So alpha equals 2 is not an exception from this construction. It is an exception from this transformation, but it's still everything works for alpha equals to 2, in the sense that the corresponding presymplectic structure is produced by variation of one form as well for alpha equals to 2. So only alpha equals to 4 gives us something different. Only alpha equals to 4 allows us to construct this nice example of a presymplectic structure that doesn't originate from variation of one forms, that is survives to the second page of the Wiener spectral sequence. Yeah, and in conclusion, I must say something about the original idea. The original idea of this construction apparently belongs to Peter Wolver. He was trying to construct a Lagrangian system which possesses a non-trivial conservation law that survives to the second page of the Wiener spectral sequence. It would be nice to have this construction. I mean, my example is not of this type, so it doesn't solve the original problem stated by Peter. But let me make some comments on the original problem. So let's suppose that we have a Lagrangian system which has this problematic conservation law, which has these problems with compactly supported perturbations within the class of an almost boundary condition. For such a system, we get the noisy correspondence given the formula 75. So we get the correspondence between symmetries and conservation laws, some symmetries and conservation laws, that is noisy symmetries, that is symmetries such that the left-hand side is variationally exact, right? And if we have a conservation law that survives to the second page, then for such a conservation law, we have 0 on the right-hand side, right? So we must have 0 on the left-hand side. But for Lagrangian systems, the noisy correspondence is surjective. I mean, the correspondence between all symmetries and all variational one forms given by this contraction. The correspondence between all symmetries and all variational forms is surjective, so it's epimorphic. This means that for such systems, the existence of such a conservation law, this was the second page, means that the correspondence between symmetries and conservation laws becomes many-to-many. Part of this many is not that problematic because we just say that symmetries lying in the kernel of this contraction operator are just gauge symmetries for the corresponding Lagrangian system, so they are trivial in some sense. We would like to treat them as trivial symmetries. So a part of this many-to-many, one of these many, is not a problem. We just say that we can describe the correspondence in the following way. We just take a conservation law, calculate its differential D1, and get a variational one form. And this variational one form corresponds to a unique symmetry modulo like gauge symmetries. So in this case, this if we consider the correspondence in this direction, the correspondence is okay, but the problem is that we have a lot of symmetries, trivial symmetries in this case, right? Gauge symmetries, not trivial, but gauge symmetries. That correspond to a non-trivial conservation law, right? The problem is that we don't have a nice correspondence between conservation laws and non-trivial, that is non-gauge symmetries in this case, because on the right-hand side we get 0 for such a conservation law. So we have a non-trivial conservation law that corresponds to gauge symmetries. Is that nice? Yes, and any Lagrangian system of this type must admit gauge symmetries. If it possesses a conservation law that survives to the second page, then of course it admits gauge symmetries. It cannot be L-normal. For Lagrangian systems, not being L-normal means to admit gauge symmetries. So in terms of Lagrangian systems, the existence of such a conservation law would mean that we have a problem with this Noether correspondence between conservation laws and symmetries, because some non-trivial conservation laws correspond to gauge symmetries, which we would not like to face in applications and all of that. Yeah, and here I have some references. This is preprint where it's written, the talk is written in a more detailed form. The original paper by Peter and Olver about the question for Noether for Lagrangian systems, the same question for Lagrangian systems. The book with general information on this machinery, and the paper by Druzhkov, which gives also some interpretation, some topological interpretation of the conservation laws surviving to the second page. Yeah, thank you.
Thank you, Kostya. Questions, remarks?
Maybe I would like to have a couple of questions. So first question, if you go to page 19, right, where you describe this variation, 19 and 20.
Okay, yes.
So here, for example, so that's the described variation. So let's go back to 19. So if you look to this heat equation and these two different, what you call almost boundary conditions, they are indeed different, right? The first one is non-characteristic, and the second one is characteristic. So if you would like to solve Cauchy problem for this thing, so in analytic case, the first works and the second not. While if you would like to pose to get semi-flow for the heat equations, and second one works, but only to one side, right? So in a sense, that restricts to you because you would like to kind of do extension of your boundary conditions, right, to integral manifolds.
Yeah, but it's just an illustration of an
no, but I mean,
condition.
if you take the first one, right, it contains two functions. It's clearly much bigger than the second one, which depends on one function. So you cannot really perturb majority of first boundary conditions to get a second boundary condition. That's precisely the question you discussed afterwards, that you can do perturbations or not, but
no, I mean, in this case, we for sure can't perturb just any function. We can include a parameter, perturbation parameter. And then we have, I mean, if we fix two functions, then we get a particular boundary condition, almost boundary condition. But I can consider functions of t and epsilon. Of course, I can perturb
if you keep your manifold ends, like if you
yes,
if you keep like x equal to 0, right? But if you would like to perturb it to different,
I want to perturb the manifold itself.
Yeah, so these are quite different things, and that probably should somehow be reflected in your formalisms, but I didn't see that it was reflected.
Yeah, it's here. It's given here. I mean, the boundary itself, the n is fixed, always fixed. N is fixed. I mean, actually, I would like to consider a situation where I do not have a bundle structure on differential equation. So the differential equation is just a manifold with an involutive distribution. In this case, I cannot use something like base space, and I cannot fix something like a submanifold of the base. That is why I have to fix this manifold actually in this situation. If I do not have a bundle structure, I cannot do something like that, something like perturbation of n. So I have to fix it.
That's correct, but I mean, your boundary, this is almost boundary conditions that actually should be important for perturbation, because if they are non-characteristic, you can actually extend to interval manifolds to
Yes.
directions. So this doesn't show up in your computations, and I don't know why. Okay, so that's
if
just
it's possible to extend it to a solution, then of course, this is what I said when I said that if n has no boundary, then we have this problem, that the description of the homotopy formula given by the homotopy formula becomes topological. We do not consider topological part of the story. But we still have the same homotopy formula in this case, so we get some non-trivial information.
My second question is the following. So, so you consider this MKDV, right? And you say you write the rational principle, but in fact, when you apply Euler-Lagrange to your second order expression, you get differential consequence of this thing, right? So, which means actually that you don't work with this potential KDV equation, but you work with these differential consequences. So you actually shall really work with fourth order equation, not third order equation.
No, I can work with the original equation itself, third order equation, and consider this perspective.
Well, it's not variational, right? So variational is
no, of course. I don't mean that the equation is variational.
Okay.
So I don't mean that it's Lagrangian. It depends on terminology. I can say that the equation is variational because it admits an non-trivial perspective structure, but it's not a Lagrangian equation. It's true, of course, yeah, it's not a Lagrangian equation.
But all the structures are actually for fourth order equations.
No, they live on this third order equation. The perspective operator lives on the third order equation. It becomes degenerate on the third order equation and non-degenerate on the fourth order equation, but I don't want to consider the fourth order equation in this case.
All right, so they're actually non-degenerate on fourth order equations. That's why, yeah, and they naturally live there. Yeah. Okay.
Yeah.
Okay, Borja, are you satisfied?
Yes.
Okay, thanks. More questions,
thank you
more remarks?
Yes, I'd like to ask. So I didn't understand the very last thing about a problem about Noether theorem.
No, it's not a problem about Noether theorem. It's just some problem with Noether correspondence. The correspondence is given as follows. We take a conservation law, we evaluate this.
What is violation?
Yes, what is omega?
Is the corresponding pre-symplectic structure. We consider a Lagrangian system. Yes, we consider a Lagrangian system. Then we have an surjective mapping from all symmetries to all variational one forms, right? And the kernel of this mapping from all symmetries to all variational one forms, the kernel is given by this, the kernel of this contraction. And the kernel is called, for such systems, it is called like gauge symmetries. Symmetries that lie in the kernel of this contraction are gauge symmetries. So the correspondence is given as follows. We take a conservation law, we evaluate the corresponding variational one form, and since the mapping is surjective, we get the corresponding symmetries, modular gauge symmetries. This is the Noether correspondence between conservation laws and symmetries. But if the conservation law survives to the second page, then on the right-hand side, we have 0. So we get a non-trivial conservation law such that the corresponding variational one form is 0, that the corresponding symmetries are just gauge symmetries. And the correspondence becomes between a non-trivial conservation law and the gauge symmetries. This is not a good situation. Roughly speaking, we get a non-trivial conservation law that corresponds to a trivial symmetry.
Well, I would not say that it is violation.
No, it's not. Not
I would say that it is generalization of Noether theorem to systems with gauge symmetries, quite natural.
Yeah, but this is not a problem of gauge nature. I mean, the violation of the correspondence, because non-trivial conservation law corresponds to gauge symmetries.
Yes.
But this is
trivial
impossible.
Yes, well, not trivial, but with trivial characteristics.
Yeah, I mean, to gauge symmetries.
They are special.
Yes. Yes,
but
yes.
this is
The violation
impossible.
of the correspondence.
What possible violation could happen?
That it is if a Lagrangian system possesses a conservation law surviving to the second page, then this conservation law corresponds to gauge symmetries. Non-trivial conservation law corresponds to gauge symmetries. This is the violation of the correspondence given by the Noether theorem, not of the Noether theorem itself. The correspondence between non-trivial conservation laws and non-trivial symmetries.
But why this could happen? There is theorem with the proof. So why you suspect that it can be violated?
I mean, if we have the situation, if we have a Lagrangian system that possesses a conservation law surviving to the second page, you mean that there is a theorem that states that it's impossible?
Yes.
Right?
For gauge systems.
Yeah, for gauge systems.
Yes, for gauge systems, yes, there is exact correspondence between symmetries model gauge with conservation laws.
With variational one forms.
Yes.
And you mean that with conservation laws as well? Like, no, the symmetries correspond to not just variational one forms, but conservation laws, right? The mapping is subjective.
Yes.
Now, okay. Thank you. I lost you about it later. Okay.
And
About the reference.
Another question: you found a nice example of non-trivial symplectic, not non-trivial symplectic form, which is not exact.
Right.
Then, in this case, there is always a Lagrangian element, an element in the corner. But then you interpret this element as conservation law for some very artificial system. Why to do this?
Because I want to construct an example of a conservation law originally.
But it's a conservation law, very strange system.
Yeah, it's true, but
your
hasn't
real
been
example
confirmed.
is example of this symplectic structure.
No, the real example is of conservation law. Of course, the example is very formal. It is rather degenerate, but it must be degenerate. I was trying to explain it. But
yes,
the existence of such conservation laws,
no.
Yeah, I mean, the existence hasn't been confirmed in principle, the existence of such non-topological conservation laws. So this example of a conservation law confirms that they exist.
Yes, but it's, I think it's not strange if the system has a non-trivial third line. And this is an overdetermined system, so...
Yes, maybe, but I mean, the interpretation shows that the result, it's not that easy. I mean, using this interpretation, you can see that it's not that easy to get such a conservation law, because for all these systems, pretty same as the original one.
Yep.
The result doesn't hold for them, so it's not that easy. It's rather natural. I would agree on it. It's rather natural, but it's not easy
the example of symplectic structure. If you have this symplectic structure, you always can repeat the same artificial.
Yes, of course. Of course. Yes.
Okay.
But I think that such phenomena arise not only in artificial examples, but in natural ones too. If an equation has three non-trivial lines.
Maybe, yeah, maybe. No.
Well, of course, maybe, yes, it needs to be clarified, but
I mean, from what I understand, this is the first example of this type. And it looks rather simple. So maybe it's one of the most simple examples of this type. It's not, of course, it's artificial. I totally agree on it. It's artificial. It's a trick.
Yes, it's
and of course, in essence, it's a story about presymplectic structure, which becomes a story of distribution law using this trick.
Well, assume that we have an equation and we consider some covering. Yes, then the system that determines the covering is overdetermined, yes?
Yes.
Yes, maybe in such a, well, this is a more natural example. Maybe for some coverings, such type of conservation laws may also arise.
I don't know.
Yes, of course you don't know.
I mean, yeah, maybe. From what I understand, this is the only known example of this phenomenon in principle. So we can just say that maybe they exist somewhere else. Of course, it's true. Maybe they exist.
I only want to say that it would be nice to have not so artificial example, but
yes, of course,
more natural ones. That's what I want to say.
Yeah, I totally agree with it. The problem is just to construct it. I don't know how to construct it in general.
Okay, more questions, more remarks. No, Kostya, thanks a lot. So next time we meet as the independent, and there will be a second part and the last part of Gosha Sharidin's talk. So thanks a lot and see you in a week. Goodbye.
Thank you.